In this screencast, we discuss logarithmic functions. Recall from our previous screencast that a logarithmic function is an inverse of an exponential function. There are many different logarithmic functions. This should not be surprising given that there are many different exponential functions, some of which are growing and some of which are decaying. Shown below are equations for 4 different logarithmic functions. We have y equals log 3 of x, y equals log 0.94 of x, y equals log 10 of x, and y equals log 5.6 of x. The letter x represents the input variable and the letter y represents the output variable. In each example, the log r is the function name. So for example, log 3 is the name of this function, log 0.94 is the name of that function, log 10 is the name of this function, and log 5.6 is the name of that function. And in all of these cases, the letter x is representing the input. Normally, we put the input variable in parentheses, but when we're writing logarithmic functions, commonly the parentheses are omitted. So for example, I could write log 3 and then put my input x in parentheses. That would be how we would be accustomed to it, but it's common not to put the input in parentheses, and so we just understand that log 3 is the name of the function, and whatever is after that is the input. For each positive number r, log r is a different function. The number r is called the base, and the function y equals log r of x is referred to as a base r logarithm. The 4 logarithmic functions above are the inverses of the following exponential functions. So log base 3 of x is the inverse of y equals 3 to the x. Log base 0.94 of x is the inverse of y equals 0.94 to the x. Log base 10 of x is the inverse of y equals 10 to the x. And y equals log base 5.6 of x is the inverse of 5.6 to the x. Notice that in general, the factor is always the same as the base. In general, the functions f of x equaling r to the x and g of x equaling log base r of x are inverses of each other. And again, notice that the base always agrees with the factor. So the growth factor r in the exponential function is the same as the base in the logarithm. Because these functions are inverses of each other, it follows that their inputs and outputs are reversed. In general, whenever r to the p is equal to q, then log base r of q will equal p. This statement says that these two functions have opposite inputs and outputs. So the p here is the input for the exponential function, and q is the output. But when I write this equation in terms of logarithms, notice that the q is now the input and the p is the output. So you can see they are opposite. Here p is input, here p is output. Here q is output, here q is input. Let's practice this relationship between the inputs and outputs of these two functions by looking at the next example. In each of the following equations, write an equivalent equation. Let's look at part A. If I told you 4 squared is 16, we should be able to rewrite this using logarithms because this equation can be interpreted in terms of exponential functions. Notice that the factor in this equation is 4. The 2 is playing the role of the input variable. The 16 is playing the role of the output. In terms of logarithms, we would say that log base 4 should take 16 and return 2 back. Again, I'm using the inverse or the reverse input-output nature of these two functions. Let's look at part B. In this case, in part B, the W is playing the role of the input, the V is playing the role of the output, and the factor is 0.87. So we could rewrite this equation in an equivalent logarithmic form. It would be log base 0.87, and now the input for the logarithmic function is the same as the output for the exponential function, which is V, and the output of the logarithmic function is the same as the input of the exponential function, which is W. Let's look at part C. Now I'm given an equation that involves a logarithm. The 1 is playing the role of the input, and the 0 is playing the role of the output. The base is 10. So if the base is 10, then in terms of exponential functions, we could say that 10 raised to the 0 power is equal to 1. And again, the 0 is the input here, which is the same as the output here. The 1 here is the output. Over here it's the input. Now let's look at part D. Log base 4 of t is u. So t is the input, u is the output, and the base is 4. Rewriting this equation using exponential functions, we would have 4, that's our factor. The input here is the same as the output of the logarithm, which is u, and the output here is the same as the input from the logarithm, which is t. Let's go ahead and look at example 10.7. Solve each of the following equations. Notice that both of the equations here seem to involve exponential functions. The variable, or the unknown, occurs in the exponent in both cases. We can solve such equations like these by rewriting them in equivalent logarithmic form. Let's try this out. We'll start with part A. Notice that x is playing the role of the input in this exponential function, and 8 is playing the role of the output. If I rewrite this equation using logarithms, I would say that logarithm base 3 takes the number 8 and returns x. So we've solved this equation. We've said precisely what x must equal. It's not the most gratifying answer, perhaps, because it's hard to say exactly how big this number is. But it is precisely correct. If x has the value log base 3 of 8, then x will satisfy this equation. Let's go ahead and look at part B. Now if you compare this equation to the one up above, you'll notice there's one slight difference. The presence of the number 8 out in front of our factor raised to a power. We've not seen that before. Before we can use the same approach as we did in part A, we have to address the presence of this 8. Notice that we can eliminate the 8 from the left side of the equation by dividing both sides by 8, and so that is the first step here. If I divide both sides by 8, the 8's divide out on the left side, and we're left with 0.93 raised to the x equaling 2 divided by 8, which is the same thing as 1/4. or 0.25. So you can see from here that x is playing the role of the input and 0.25 is playing the role of the output. I can rewrite this equation in an equivalent logarithm format, and I would say log base 0.93 of 0.25 is equal to x. So again, we've solved the equation. We've said precisely what x must equal in order for x to solve this equation. The solutions that you obtained above are exact. In real-world situations, however, it may be preferable to obtain a decimal approximation. Your calculator has a log button, which enables you to determine decimal approximations for base 10 logarithms. If you look at the solutions above, however, none of them are base 10 logarithms. So we will need to convert these logarithms into base 10 logarithms. To do this, we use the change of base property of logarithms. The change of base property says that the logarithm base r of a number x can be calculated by using base s logarithms. I take log base s of the x value and I divide that by log base s of the old base r. This property converts base r logarithms into base s logarithms. Although s can be any positive number, we will take s to be 10 because we want to convert all of our bases to base 10. To illustrate, suppose you want to find the decimal value of our solution from the example above. We rewrite log base 3 of 8 as follows. So log base 3 of 8, notice I'm converting it into log base 10, log base 10. I take log base 10 of my x value and I divide by log base 10 of my old base, which was 3. On a calculator, you would press your log button and then type 8 and close the parentheses. Then press your division key and the log key again, then press 3 and close the parentheses. When you hit enter, the graphing calculator will give you a decimal approximation of 1.89. We can also use the change of base formula to work out a decimal approximation to our other example above. If you recall, when we solved our equation, we arrived at x equals log base 0.93 of 0.25. If I convert this into base 10 logarithms, I get log base 10 of 0.25 divided by log base 10 of 0.93. Working this out on a calculator, we find we arrive at a decimal approximation of 19.10 to two decimal places. One final note. For base 10 logarithms, it's standard practice to write log x rather than writing log base 10x. Base 10 logarithms are used extensively in the sciences and are generally referred to as the common logarithm. So it's important to understand if ever you see a logarithm and the base is omitted, you assume it's 10. So in our calculation right here, we could have just written log of 0.25 divided by log of 0.93. This is how it would be more commonly written. Let's go ahead and look at example 10.8. E. coli bacteria divide every 20 minutes or every 1/3 of an hour. Assume that we start with a single bacterium right now. Let's look at part A. Determine an equation for the function that calculates the size of this population after t hours. Well, notice that the bacteria divide every 20 minutes. That suggests that the population is doubling in size every 20 minutes. If the population is doubling in size, that corresponds to a factor of 2. Now, it's growing by a factor of 2 every 1/3 of an hour, so that suggests that our delta x, our time period, is 1/3 of an hour. Because the population is growing by a constant factor on equal time periods, that suggests that the population growth is exponential, and therefore it would have an equation of the form y equals b times r raised to the x over delta x. Now, the y variable in this example, the output, would represent our population. So we might decide, instead of using the letter y, we might instead use the letter p to help us remember that the output is a population. The input variable x represents time, so we might decide, instead of using the letter x, we might use the letter t in its place to help us remember that that variable represents time. The other part of this equation that we haven't discussed yet is the value of b. If you recall, b represents the y-intercept, or the vertical intercept, or alternatively, it represents the initial amount. And for us, the initial population size, since we're talking about a single bacterium, that initial population size must be 1. So if we fill in all of the information into our template equation, we arrive at an equation given by p equals 1 times 2 raised to the t divided by 1/3. Now, this exponent here is rather complicated. Let's simplify that. The exponent is t divided by 1/3. I could also write it this way. Dividing by 1/3 is the same thing as multiplying by the reciprocal. So in this case, that means multiplying by 3. And so our exponent, when simplified, is 3t. So our equation is p equals 2 raised to the 3t. So this function illustrates how this population grows. Now let's look at part B. For the function you created in part A, determine the inverse function. So let's start with our formula, p equals 2 to the 3t. You'll notice that this is an exponential function, and 3t is effectively playing the role of the input, and p is playing the role of the output. If I want to determine the inverse function, that means I want to solve this equation for t. Solve for the input variable. And notice the input variable is inside an exponent. But we can rewrite this equation using logarithms. Notice that the factor is 2, so the inverse function would be log base 2. And now we reverse the inputs and the outputs. So I would say log base 2 of p is equal to 3t. Solving for t, I would divide both sides by 3. So that tells me t will equal log base 2 of p divided by 3, or alternatively, instead of dividing by 3, I could multiply by 1/3. So this is our inverse function right there. Let's look at part C. How long will it take until the bacteria population equals the number of humans on the planet, which we'll say is 7 billion? Well, notice that this is a how long will it take kind of question. So we want to use a function that has the capacity to answer that kind of question. Which of these two functions is best suited to answer that question? Well, if you look at the second function here, it's set up to calculate time periods. It's set up where we put in a particular population size, and it calculates how long it takes to reach that population. So in this case, we're looking at a population of 7 billion. That's 7 times 10 to the 9th power. And we want to calculate how long that will take. So if we substitute 7 times 10 to the 9 in for p in our equation above, we get t is equal to 1/3 times log base 2 of 7 times 10 to the 9. To get a decimal approximation of this, we take the 1/3 and we multiply it by log base 10 of 7 times 10 to the 9 and divide by log base 10 of 2. We've just used the change of base formula right here. That's where this is coming from. And if we work this out on a calculator, we find we arrive at approximately 10.9 hours. So that's how long it will take until the bacteria population equals the number of humans on the planet. Now let's go ahead and look at example 10.9. Consider the functions y equals 2 to the x and y equals 1/2 to the x from some previous examples. Part A, let's determine the inverses of these two functions. Well, let's start with y equaling 2 to the x. This is an exponential function. Its factor is 2. The inverse of this function would be log base 2 of x. If we look at y equals 1/2 raised to the x, this is an exponential function with a factor of 1/2. The inverse would be log base 1/2 of x. Now let's look at part B. Shown on the next page are the graphs of the diagonal y equals x, y equals 2 to the x, y equals 1/2 to the x, and their respective inverses, log base 2 of x and log base 1/2 of x. Our goal is to match each graph with its equation. Okay, so here are the diagonals. Here's y equals x in that graph, and here's y equals x for this graph. First of all, can you find an exponentially growing function? Well, you can see here that this is the only curve that has the right kind of behavior for it to be an exponentially growing function. So that means this must be the graph of y equals 2 to the x, because that's an exponentially growing function. If this is the graph of y equals 2 to the x, notice that this graph, which is the mirror image of this graph, this one must be the inverse. So therefore, this graph must have equation y equals log base 2 of x. Now let's look at this curve. This is an exponentially decaying curve. So it must have equation y equals 1/2 to the x. And if you notice the gold curve here and the diagonal, notice that what you're seeing on this side is the mirror image of what you're seeing on this side. So this gold curve here must be the inverse of y equals 1/2 to the x. And that would imply that this is log base 1/2 of x. The example above illustrates that there are two basic types of logarithms, ones that increase, like this one, and ones that decay, like this one. Logarithms corresponding to exponentially growing functions are increasing, while logarithms corresponding to exponentially decaying functions are decreasing. So notice that when the exponential function is growing, so is the corresponding logarithm. If the exponential function is decreasing, so is the corresponding logarithm. This is illustrated in the figure below. So here's a graph of an increasing logarithm, just like the graph above. We arrive at a graph like this when we start with an exponentially growing function, and we have an exponentially growing function whenever the factor r is larger than 1, or alternatively said, if the base of your logarithm is larger than 1, then you're going to have an increasing logarithm. This logarithm is decreasing, just like this one up above is. So you arrive at this kind of a logarithm by starting with an exponentially decreasing exponential function. And you get exponentially decreasing functions when you talk about factors that are smaller than 1. In other words, if a logarithm has a base that's less than 1, it's going to be a decreasing logarithm.